like I said, today, this week, we're looking at computer vision applications of transformers. Mixer is not actually a transformer, but it basically uses some concepts from the vision transformer. So I thought that would be pretty cool to cover. A recap of transformers. So transformers are made up of transformer blocks, and each one of these are called transformer blocks. And the main thing in a transformer block is attention. And what attention is basically just this equation, which multiplies query and key together, and then you multiply that by a V value. And you calculate Q and K and V by multiplying the original input by a weight factor. And you can usually think, I saw a pretty good analogy on Reddit the other week. They said query key are kind of, if you imagine transformer, the attention as like a dating app, then query key would be the different characteristics of different people looking for each other. And then if they match, then the query key value would be very high. And if they match on something important, the value would be high on that end as well. So the more attention there is, the better it is between those two particular variable. And usually when we talk about variables, we usually talk about like the different words in a sentence that relate to each other. There's also multi-headed attention, and we use multi-head attention just so we can encode attention for different contexts. So for example, in the original transformer, I'm pretty sure there's like around 6 to 8 heads of attention. It's basically just this, but 6 to 8 times. And one of those heads would be probably for training for grammar, and the other one would be training for code vocab. We don't know, we don't control it, but it does train different contexts of words in a sentence. So that's pretty cool. And another important thing within a transformer is these positional encoding that we will also talk about in other models today. This positional encoding is not actually trained. It's just a fixed static equation of sinusoid function. So for even number words, they'll use this equation, and for odd number words, they'll use this equation, and it does positional encoding pretty well. It basically tells the model relatively which word is next to each other, which words are far from each other, etc. And we use positional encoding right here, just right when you input these words. Notebook time. So this week we're looking at a BERT notebook for multiple choice. I don't know where it is. Okay. So it's in a link posted in the Discord channel that I linked. So we're looking at week 3 BERT QA easy. I tried to train a different data set and it didn't work. So I named this one easy because it did work. This data set is called ArcEasy. It's basically a grade school multiple choice data set. You don't supply the machine learning model any context of the question. You just supply the question and a few multiple choice answers. And since BERT is a pre-trained model, we're hoping that it can understand the question and be able to provide a good enough answer. And we'll probably see in later sections of this that it doesn't actually train very, very well either. And I think if to train a better model, we will have to have context. And in some other data sets, they would usually provide a question and a paragraph of words, so you can extract some words within that paragraph to choose an answer. But this one doesn't.
Interesting. So what exactly is in the question? Or their labels and their choices, I see.
Yeah, so question and then choices, and then there's also like a label thing that's kind of annoying because some labels are A, B, C, D, some are 1, 2, 3, 4. And yeah, it's just annoying to deal with when we're cleaning up data. I also did like some really basic data analysis. The lengths of text are, yeah, this is distribution of the lengths of texts, and I think I cut it at a very small number. I definitely defined max length somewhere. Max length. Oh, 80. Yeah, so I just cut it right here. I don't think there's anything that's beyond that number of words. So,
Oh, so
and
that's essentially like the size of your weight matrix?
oh wait, actually, let's roll back.
Oh,
This
sorry.
80 as in all 5 answers added together has a total length of 80. So each one would have like very not a very large number of words. I did that because my computer doesn't have enough space for training larger amount of words. So this time we used BERT tokenizer to tokenize our words. Oh no, I just used the auto tokenizer, but we used a pre-trained BERT tokenizer. We
Is
also
there a heuristic behind the tokenization, or it's like also just a trained model that does the tokenization?
it's just a trained model, and it's provided by the Hugging Face library, which is very
I see. So it's not like some sort of like heuristics.
no, uh but usually for BERT it's you don't train it from scratch because BERT is basically just transformer but pre-trained in a certain way. So when we talk about BERT, it's usually pre-trained to a certain degree. To some, and then for each data I encoded by okay, so since there's a question, there's an answer. And as we can see here, some questions have 3 answers, some questions have 5 answers. I have to pat some of the answers to 5 if the answer length is not 5. So that's what we're doing here. And for these tokenized examples, I'm basically just putting them all together and all the answers together. No, sorry. I'm repeating the question 5 times to match with each answer and then throwing them into a model. And I think there's a picture here that can describe what I'm describing here. This is from week 2. Okay, it's what we're doing is for every answer, we're concatenating a question to it. And then for each of the question answer pair, we'll throw them into the model. And then we'll extract a score and we'll take the best score. So that's basically what I'm doing here.
I see. That makes sense. Process data.
This is just basic some processing. And in here, I'm just declaring a data set so I can process the words and encoding, which we talked about. Just declaring stuff. And I used the BERT for a multiple choice model. They basically defined it for us.
Oh, there's a BERT multiple choice model already?
Yeah, there's also like BERT for classification, BERT for whatever. It's pretty good.
Cool. Sounds good.
And just some basic epic, and then take the arch max, take a look at predictions, we calculate some metrics, and then in test we also calculate some metrics. And in this case, we actually can see some really not good stuff. We call this overfitting because the train accuracy is increasing to 1, which is like the best, but the test accuracy is not actually increasing by a lot. And I guess at this stage, the BERT model is just memorizing the answers from the input that we give them. And in later part of this session, I'll talk about how to deal with some overfitting cases.
Oh, is it training still done through like backprop in transformer case?
Sorry, what?
Is it still like how does the optimization works for the transformers? Is that same as just like any other neural net, just does backprops?
Yeah, it just does back propagation. And I think for the optimizer for transformers, we usually use the Atom W optimizer.
I see. I mean, it's not like I know what that is, but interesting. Cool.
Yeah. So this is just I forgot what this is called. Confusion matrix. Yep, confusion matrix. And we can see that I'm visualizing the results of test database. It's okay-ish, like it's predicting the right answer most of the time, but a lot of the times it's also predicting the wrong answers. So
it's more of like, well, I guess it's more than. I guess it's wait. Is this the validation set or the test set?
this is the test set. I did not train with the test set, so
Right.
it's data that hasn't seen before.
What's the correction rate? What's the like percentage of it?
50%, around 50.
That's better, right? Because if you have multiple choice, on average, you should get like what?
Yeah, it's better than random guessing, but it's still not like optimal.
Interesting.
Okay, and that's really it for notebook. I trained them some weights if you want to use this overfitted weight for anything. It's in the Google Drive link that I sent in the Discord.
So this is just like trivial like BERT models?
Yep, this is a BERT model.
So I suppose we're going to look into like what kind of other model we're going to do.
This week we're just doing vision transformers.
Oh, interesting.
When we look at normal transformers, we usually input sequence data. So for example, text, audio, and like stuff like that. We input word one by one, or in audio, you might input the amplitude one by one. Mm-hmm. But when we think about computer vision, we don't really think of one image as a sequence. They're not sequence. So how do people use transformers in a computer vision context? Well, they basically just split the image into patches and then throw them in as a sequence. And the reason that they cannot, say, put each pixel, flatten the whole image and then put each pixel into the transformer is that if you remember, actually you don't remember from previous week, but for transformers, since we have the attention mechanism, all the memory efficiency within the transformer would be O(n) squared. And when we think about just 100 by 100 image, it's already 10,000 times 10,000 memory requirement, which is a lot for such a small image. And with really, really high resolution images these days, it doesn't really apply. So that's why the authors of this paper decided to split the image into patches, and then we throw these patches into the transformer.
See, I don't think I exactly follow. So it sounds like some internal mechanisms within the transformer attention layers are having this like exhibited this like O(n) square space usage.
Yeah. So actually, I have a graphic from previous week. So this thing, this is basically an English to French translation data set, and this is one of the attention blocks visualized. And for each word in the sentence, it would have attention to every other word in the other sentence, of the output sentence. And that's why there's n squared memory requirement.
Oh, essentially it's a matching matrix. I see.
Yeah.
Essentially like adjacent. So it's a graph. Essentially it's the adjacency matrix
Uh,
ish? Not exactly.
Not exactly, but
Not exactly. Right.
it's correlating with each other within. So it's like a grid. So that's why
I
it's n squared.
Wait, so okay, so in the image case, why is it bad? Because like what's like so the input, like for the translation case, the input is English language, output is the French language, right?
Mhm.
So that's like input and output. So for a VIT, like what's like it seems like the input is the image itself. What's the output that we're trying to do?
Output, we can actually do plenty of things with the output. So in this base case, they're just using it for classification.
I see.
But if you switch out this head, kind of like other vision models, you can switch out the head and then throw another linear layer in. You can do regression tasks with it as well. And
Regression task or like interesting.
yeah, so regression is just a linear classification task, but the output is from 0 to 1, right?
Okay, right.
Yeah,
Interesting.
and then you can also do like less amount of classes. It's, as long as you switch out the head, it can be reused.
So in this case, if I have an image, if I just like trivially flatten it, so 100 by 100 matrix, that's 10,000 columns with times number of classes output. Is that correct or no?
No.
So
Okay. So it's just if you put in one image, it's just and you're classifying for 5 classes, it's just 5 classes output.
I see.
Because yeah, we're only using one, and we're not using each patch as a classification model. So there's we're grouping them all together and then deciding on a final outcome. And so for each of these patches, we linearly project it, and usually that means a dense layer that can be trained to kind of extract features within these patches. And we also add a positional encoding thing here after you project it to weight a representation of those patches. And basically, these positional encoding different from the base transformer. This is actually trainable, and for each position within the image, we have a different weight. So each time for like different images, we'll use the same weight for the same position. So imagine it as like a dictionary. So
wait, is it different weight? We're gonna be using a same position?
Sorry, it's a trainable weight.
Okay.
And for the same position, we'll use the same weight every time.
Right. Okay. Makes sense.
Yeah. Sorry. Yeah. So that's what positional encoding does. It doesn't use the sinusoid encoding anymore.
Right.
And for the transformer encoder, it's basically exactly the same as the base transformer. It's just only the encoder part. And this paper does a good job of explaining what they did in order to fine-tune their model. And for example, they use regularization. And regularization is very important in terms of solving overfitting problems. So they specified these 3 as the ones they used. So first of all, in weight decay, the purpose of weight decay is prevent the gradient from exploding. And whenever the gradient explodes, the model does not train well. So does that make sense?
Exploding, what does that mean exactly?
That means the gradient. And remember, every model backdrops, and then there's a gradient that you subtract from the original in order to get closer to the global minimum rate. Right. So whenever the gradient is too big, it's called gradient explosion. It's not natural, and it basically does not allow the model to converge well.
So essentially, the model just start like swinging, like big swings in terms of like losses.
Yeah, and so in weight decay, you're trying to You put a. Do you know what a loss function is?
Yeah.
Yep. So loss function is basically the thing that you were trying to minimize within the model. And in weight decay, you put the weight term within the loss function, and you try to minimize that as well.
Oh, I
And
see.
yeah,
You're minimizing the weight itself too as well.
yeah. But you also multiply that by a hyperparameter, so you don't minimize it too much.
Right.
Dropout. It's very classic. You're basically disabling some nodes in order to train other nodes better. So an analogy that I would usually use is if you're left-handed, you tie your left hand behind your back and try to use your right hand to write for the day. That's dropout. And they also used something called label smoothing. And what it does is, for example, in classification, if you have 3 classes, usually the vector representation of the result is 1, 0, 0, or 0, 1, 0, something like that. The correct class is always 1. The incorrect classes are usually 0. And in label smoothing, they are basically making the correct class not 1. Like it would be something like 0.9, and the incorrect classes would be 0.03. They still add up to 1, but basically smooths out the labels. And the reason for doing this is it prevents erroneous data from messing up the model. It makes the model smoother when training.
Interesting.
That's
interesting. Okay.
I think one of the things they used for searching for the optimal hyperparameters is grid search. Grid search, it sounds difficult, but it's just a for loop. You for loop whichever values that you want to test, and then you
hyperparameter search.
Yeah, you pick the best ones, and they use that to search for the best learning rate. And we talked about the transfer learning stuff earlier when we were talking about the output. But basically, when you trained up the model, you can remove the head and then throw in something else and then train it just a bit more to achieve a pretty good result. And
the head, is that the one that's like the final linear layer that does the classifications?
Yeah, that's right. That's the final layer.
I see. So you maintain exactly the same layer for encodings and then the attention layers as well.
Yeah, that's right.
I see.
And they mentioned that they tried to initialize the linear layers with some distribution didn't work, and they found that 0 initiated is actually better.
Interesting.
They also use pre-training, and I find this very interesting because basically what this is doing is they didn't use the labels for pre-training. They removed some patches within the transformer when training. Within the image when training. They replace that with mask. Sometimes they will replace it with random sometimes. And then in those replaced patches, you're trying to predict the mean color of that patch. So you don't need any labels for doing this pre-training task. You're just trying to predict a missing patch that you know what.
So is that means like it's effectively making the model have a better contextual awareness of what the image represents?
That's exactly right. Yeah. It searches around the image, around that missing patch, and they decide what that patch should be. And this is pretty familiar pretty similar to what BERT does in MLM. They also just mask out some of the words and predict what word that is.
Yes, multi-level marketing.
Yes, this is, I forgot what it's called, a mask. I forgot. Yeah, I don't remember what this stands for anymore. It's mass something modeling. Oh, mass language modeling? I think, yeah, it's mass language modeling.
That's actually interesting.
And these are also some of the experiments that they tried in finding out the best parameter to tune when they're deciding how many layers they want to put in the model. So in 10 to the power of 0 is the base model, and these are the base numbers. and they tried to increase it by a factor of something for each of these parameters. And they found that whenever you increase the patch size, it improves the model by a lot. Like for all the parameters, if you increase something, it always improves the results. But especially for depth, it improves more for those guys.
Is the y-axis the accuracy?
Yes, that's what I will be explaining now. What a 5-shot means is you pre-train the model using another data set, and then they look at ImageNet, and for each class they have 5 samples to look at, and that's their accuracy. So they don't use the full data set, they only use 5 examples for each class.
I see. So I guess the application behind that would be like, I don't know, online learning or something, or it's like iterative learning.
It's for showing off how good they are when trained on a small sample size.
Interesting.
Yeah.
Right, makes sense.
And more experiments. So in the vision transformer, you would notice that the first position is not occupied by any patches. We call this the CLS tag, also class tag. And basically, when it's at this position at the output that we extract the final classification from. So this connects here. And the other method of getting the output is called global average pool. You pull together all the layers from other patches and then get a result from it. They decided to use the CLS method in the end because they thought it worked better, but upon further examination, they realized that if they tune the learning rate to the right thing, global average pool actually performs around the same as CLS token. You just have to tune it well. So green and blue here.
What does each one mean exactly? Like, this is like the polling layer in the end?
Yeah, there will be a polling layer in the end to extract all the stuff. It's
so that's like global
averaging them.
Yeah, I guess like global average pooling, just like for all the patch, pull everything together, take the average of everything.
Yep.
Then what is CLS then in that case?
CLS, all of these layers are still interconnected somehow, but they're only taking the first thing, which is the CLS token. They used it in BERT as well. So you would see that the first spot is also just CLS, and they take this as the output.
Oh, I see. They just directly take only one value.
Yeah.
I see.
Yeah.
Interesting.
That's right.
Interesting.
And for positional encoding, they actually tried a few different methods. So there's like 0, 1D, 2D to relative positional encoding. So for the first one, there's no positional encoding. So basically what you're telling the model to do is you throw them a bunch of patches and you tell the model to do whatever they want with it.
So there's like no like position information at all.
Yeah, they just don't know. It's just a bunch of patches together. For one-dimensional, we're rolling the patches out and we're numbering them from 1 to whatever max number. And for 2D, it will be taking in consideration of the y-axis. So 1, 2, 3, and then the second row 1, 2, 3, third row 1, 2, 3. They also tried relative attention. It's just how far each patch is relatively from each other. They used a query key thing for that. But in the end, they found that one-dimensional positional encoding actually performed better than the other ones. And of course, without positional encoding, it performs the worst.
Interesting. Interesting. The relative attention idea seems very neat. Essentially, like given a query, figure out where in the picture this would have been or something.
Yeah, relative attention is also used in, which one is it?
The language model too as well.
Not this one. I think it's the okay, Transformer Excel. This one they used a relative attention because if you look at the full attention, it's too big. So this is relative attention.
Interesting.
And one thing that vision transformer does better than normal convolutional neural networks is that they have a wider receptive field from the beginning. And when we talk about the receptive field, we're talking about which pixels the layer is looking at. And when you think about a base convolutional neural network, from the first layer, you're looking at probably just the pixels around a specific pixel. And for each increasing layer, you will be able to look at more pixels around it because you're convolving and you're pulling the layers, right?
Right.
And in Vision Transformer, right off the bat, you're able to look at pixels from very, very far away. And then in the end, you converge more into other pixels. But this is the main advantage of Vision Transformer is that right away, they can look at other pixels and be able to form attention around it.
So it essentially means with less layers, it has better perceptive field compared to CNNs.
Yeah, that's right.
Interesting. But isn't there techniques in CNN by increasing strides, you can effectively make the perceptive layer larger?
You can increase it, but it doesn't perform particularly well.
Interesting.
Yeah. So there are definitely problems with Vision Transformer. So when we look at smaller patches, you would be able to see each patch better. But then that would also end up in a lot of patches. And when there's a lot of patches, there's also the memory problem. And when we look at large patches, we cannot identify a lot of details within that patch. So that kind of loses some of the information within the patch. So there's a balance between
VIT some sort of like lossy model where if the attention or patch is too big, it just drop out the detail. Oh, that's interesting.
Yeah. So the Swin transformer kind of solved the problem of that problem.
Oh, interesting. Okay.
So there's a thing called Swin Patches. We are splitting the patches into very, very, very small patches first, and then you're grouping them together for larger patches in later layers. And for each increasing layer, you're increasing the number of channels. And it's kind of like a convolutional neural network where for each increasing layer, you're increasing the amount of channels. So the amount of depth within it. And you might be wondering, we just mentioned that there's a problem with a lot of tiny patches because then the memory problem would get the memory requirement would get really big. And what they did was they used local attention. So they only attend to the patches within a certain range to the local patch, to the current patch. So they don't look at the relationship between all the patches around it from very, very far away. They're just looking at ones around it. And they also use shifted attention. So when we do a first pass, we use a normal partition. And for the second pass, they shift the window slightly. So we can look at different patches. We can look at different pixels within a different patch.
I see. So essentially, it's like what CNN did to the original feed forward, where it does. I do
It's
see a
more
lot of
local. Yeah, it does more local stuff. Yeah, and it is kind of similar to CNN, but it
interesting.
uses attention backbone.
Interesting.
This is just some results. Like it performs better than the VIT model, which is a variation of the vision transform. And they also decided that the Atom W optimizer is better suited for this model than SGD.
Is there like a very TLDR reasoning behind why Atom W is better than SGD?
Atom W is just a fast way of I think they didn't explain why. It's just like experimentation.
So it's an empirical result.
Yeah, based on their results.
What's the difference, or just Eli 5 me? Like, what does Atom W do?
I don't think I can explain it, but let's search it up because we have time. Atom
Not
W.
probably. Oh, that one. Yes. Nice.
Great influenza. Yeah, I don't think I can explain it. No. Well,
Interesting. Oh, it's okay. We can look it up later.
yeah, we'll look it up later. And the next paper that we're going to look at is called MLP-Mixer. And basically what the authors think is that in these vision transformer model, the attention is not giving it giving it the accuracy. It's the patches that's making it good. So they wrote a paper called "Patches is all you need." They're saying that you just need patches. You just need to split the image into patches, and we'll use just basic convolutional layers slash multi-level of perceptrons to solve a classification problem.
Wait, so are they just ditching the attention layers by using the patch, but throwing to?
Yeah. So the first paper here is called MLP-Mixer. It's actually composed by some of the authors in the vision transformer paper. That's how I'm also covering that. The MLP-Mixer we'll cover it later, but I'm covering MLP-Mixer first because the architecture is very, very similar. Basically, what it's doing is it's splitting an image into various patches. We throw them into a mixer layer, and what a mixer layer does is it looks at these patches from a channel level. You transpose them, and then you look at these patches from a pixel level. And between these transposes, we throw in some multi-layer perceptrons. So it's basically just some dense layers / linear layers between them. And you don't even need to use CNN for this. This is just pure dense net and plus patches. And it actually performed pretty well. This is some of the results. This is Mixer compared with Vision Transformer. There's various configurations of the Mixer model, but for direct comparison, the Mixer model is just right below the Vision Transformer, and we don't even need the attention mechanism for anything.
Well, that's interesting.
Yeah.
But it does develop its own way of the MLP stuff, right? Instead of attention, it does this. I couldn't quite grasp what exactly that's doing now. Yeah, this part, like channel
think of it. This is the main part. Mixer. It's just mixing stuff together. You're getting patches, throw them into something, transpose it, throw them into something, transpose it.
So channels, are we talking about color channels, RGB channels, or we're talking about something completely different?
The first layer would be RGB channels, but starting from the second layer, it will be the whatever you output, because it will not be like colors anymore. You'll have more channels. Yeah, it's just mixing it to get the pixel configuration, to understand the pixel configuration like around them more by mixing them up.
Interesting.
Yeah. So this is the MLP-Mixer model. And this is the conv-mixer model. It's basically the same thing, except we don't use MLPs for anything. We're using convolution layers.
Back to convolution again.
Back to convolution again. Yes. And yeah, there's depth-wise convolution to mix spatial locations and point-wise convolution to mix channel locations. It's just mixing stuff. It's the same concept, except they're using convolutional layers, except of dense layers. And one interesting thing is that they were able to implement this whole model using beneath the size of a tweet. So you can fit the whole model into a tweet. And they're saying, wow, this is so easily implemented. It's so cool.
Wait, but this is like very like compact, like Python less comprehension.
Yeah,
I would say
very compact. They also provide this more readable form.
Okay, yeah. Okay, that's better.
It's still very short compared to Transformer, which is a lot of work.
Interesting. There's a computing batch norm sequential of a residual. Oh, it's a residual. Interesting. Sequential. Oh, I see.
Oh yeah. Different from the original MLP-Mixer, there's a residual connection. So we saw a residual connection before in ResNet. It's the same concept. You're putting image data back into the pipeline just so the model doesn't forget it later on.
Interesting. Yeah, right. That makes sense. So it's basically significantly reduce number of parameters. We're talking about the hyperparams here?
It doesn't exactly reduce the number of parameters. It's just telling other people that they don't need attention anymore.
Right. Interesting. So they just ditched. Interesting. That's
I don't think like attention mechanism would be ditched anytime soon, but it's just a way of saying, oh, hey, this also works. Maybe some research can go into this area. It's kind of like that. So
like saying that like attention is not the key to the model, but it's the patching.
Mm-hmm. So we can see the conv-mixer here. It's like slightly less parameters than the other models. And accuracy is still very much comparable with them. There's this REST MLP thing here. It's basically like MLP-Mixer, but in MLP-Mixer, it's the paper is made by Google, and the REST MLP paper is made by people from Facebook, I think.
Mm-hmm.
It's the same concept. They're trying to ditch convolution layers with multi-layer perceptrons.
Interesting. Cool stuff.
VIT is just another variation of vision transform. I think I would cover that next week. ResNet, we all know what ResNet is. But one, I guess, drawback from using conv-mixer is that the throughput is significantly lower than other models around the same size.
Wait, are we talking about inference or training?
It's inference. So basically they're saying it's slower when it comes to inferencing. And
what's the compute stuff underneath, like tensor or GPUs? What is it?
You mean this number?
Yeah, like this, what's the
image per second?
Oh, no, I'm just wondering, like, what's the inference? Like, what's like a tensor core or something?
I think we might be able to find that in the paper.
Interesting. Yeah.
Single RTX 1000 GPU.
I see.
Yeah, so it's just slower when it comes to inferencing.
So we're looking at what, like 80?
Yep.
Wait, what's that for mean? Like 1536/20 versus 768/32.
I think I made a note somewhere. It's just like depth versus number of patches, I think.
I see.
I think
Interesting.
I made a note here. Oh, I didn't add week 4 yet. Do I have? Next week would be covering Mixer. Notebook will not cover that this week, but I did make a note of the, where is it though? Dimension is dimension is the first number, depth is the second number.
Dimension in terms of like patch size, I guess, or
no, it's not patch size. It's more like, it's kind of like the hidden, how many dimensions are there in the hidden dimension.
I see. So those are like MLP-Mixer, like,
yeah. And the depth would be, I think, the number of layers.
Layers in terms of like number of like blocks, I guess, like of those like mixer blocks.
Yeah.
I see. Interesting.
And all that's left for today is this thing, this notebook. I chose a different data set for this because I want to do some regression tasks. It's a pretty interesting data set. It's called pet popularity. It's basically, you're trying to predict how popular a pet is based on their image. And the popularity score is just statistics from a certain website, pet adoption website. Let's look at that notebook. Regression, this one. And we're using the Gradient Transformer for this. But we're still using the Hugging Face library. So it's just an import and use the model.
Interesting.
So we did use a pre-trained model of patch size.
The VIT one?
Yeah. And then the modifications that we made was, this one is just kind of modifying data. It's called data augmentation. We are doing some random rotations, random color flickering, just to make the model more robust to prevent overfitting.
Oh, this is like to the training set, I see.
Yeah, to the training set. And we needed to resize the image to a certain size so they can throw into the pre-trained model.
Okay.
This is just loading the pet data set. We have to divide the popularity score by the max. I think it's 100. I don't know why I did 20 here. It's definitely 100. 20 is wrong. And then this is the vision model regressor. So basically, we have a pre-trained model. And then we're replacing the head with some linear layers. So hidden size, we're converting the hidden size to 64 and then 64 to 1. And from this 1, we'll take the regression score. And we also added a dropout here. This one, not sure if you caught it during the presentation, but I did mention that a 0 initiated head would be better.
Right.
This is not supposed to happen. You're not supposed to initiate with a serial uniform transform. It's just that I don't have time to train another model without initialization because training takes time. This is just declaration of the data sets of regressors.
Yeah.
Remember the Atom W optimizer that we don't know much of. Yep. And some basic stuff, except we are using MSE loss this time because we're doing a regression task. And yeah, this is basic stuff. I trained 15 epics because,
How long did it take
and
you the training for you?
sorry, what?
How long did it take to train it for you, like time wise?
I don't remember for this one because I uh, I think I might have that in, because sometimes I print out the amount of seconds taken to train something, but sometimes I don't. Okay, this one I didn't either. Yeah, I don't remember, but I think I usually just leave it running overnight.
Oh gosh. Oh,
Yeah.
you train on your own machines or is it on the Google like collab or something?
The problem with Colab is that they don't offer like a free GPU anymore. They do, but then you can't train it for long before they disconnect you,
I
and you
see.
also have to line up for something. I have like okay-ish. I use a gaming laptop, so I just use the GPU on that.
With CUDA support, I guess.
Sorry, what?
With like CUDA.
Yeah, but CUDA. Well,
Actually, can you train
there.
stuff on an AMD GPU nowadays or no?
On what GPU?
AMD GPUs?
I'm pretty sure you can. Yeah.
Oh, interesting. That's very interesting, actually.
And we see a more healthy accuracy and loss curve here. Loss is
Right.
just consistently decreasing. Accuracy is increasing with the test accuracy. I'm pretty sure if I train it more, it will reach a better score, but I just stopped it because I don't have a lot of time to train.
Yeah. Makes sense. Makes sense.
So what I'm doing here after that, I saved it. I redeclared the model because I wanted the attentions. I wanted to visualize the attentions here. So I redeclared it so that it outputs the attention stuff.
Mm-hmm.
I loaded it back, and basically I got the attention.
Okay.
And these are some of the visualizations of the attentions. This is of just one specific head. Oh wait, no. I averaged out the layers within the attention, and then I took 12 all 12 heads, and then I just printed it out here, and you can see some of them, they're not really paying attention to anything specific, but you can see that in this one it's paying attention to the eyes of the cat, if you can see, and for this one it's the ears. Yeah, it's just visualizing attention. Sometimes it might not point to things that we're looking at. Like this one is just the floor, but maybe it's useful for other images where they have text in the background.
Interesting.
Yeah. And yeah,